All right, let's get started. So I've just set office hours, and so those are posted on the Canvas site, but it'll be Mondays and Tuesdays at 4:30, Monday in my Brickyard office, which is kind of down the street here, and Tuesdays in my Wrigley office. And so then if those don't work out, then my appointment is also fine. And then once we get kind of the transients die out from the semester, then the TA should also have office hours, Taha. So that'll be also be posted on Canvas when that happens. So, right, so let's get into it here. So we're talking about an introduction to modeling here. And there we go. So from last time, what did we just say? What is a model? What is the most general definition of a model? Answers a what-if question. So I was going to say, so models don't have to be mathematical, they don't have to be computational, they just have to answer a what-if question. And so gave it different examples of models. And so there's, fashion models. That supposedly answers a what-if question about what if I were to put on this, clothing. Well, I don't know what it'll look like on me, but maybe if I look at it on somebody else, I'll get a better idea than just seeing it hanging on a hanger. Now, of course, there's degrees of freedom there that can be misused. So even though you think you're just, looking at the fashion, they have been convinced that maybe the fashion might look different on you because they end up putting it in a model that reflects something else that you might like to look like. And so we have to, and those are effectively the assumptions of our models. And so we have to be careful about what assumptions we make because we can end up having really good looking results that end up not being a function of whatever model or policy that we suggest, but more about the assumptions going into it. So if you were talking about evaluating a sustainability policy, you might come up with a really interesting policy and then you simulate it, but if your simulation has assumptions that are unrealistic, then the results that come out that might look favorable actually end up being results that can't be trusted because the assumptions don't really match reality. Similar to fashion models that all look, exactly the same. So if we don't look like these fashion models, then we maybe can't trust the way the fashion looks on them. Similarly, even something, down at the very other level of, the physical models of the electron or an atom. So those sorts of things, they give us some ability to answer what-if questions about, well, what happens if I put two objects together? What are the sort of forces that we could imagine, or even the term force is a model. But we know that these are imperfect as well, and they only go so far in their precision. And so came up with a variety of different examples of things that answer these what-if questions. We're going to be drilling down into that a little bit more. So how did we say that, like this example, this mouse here that is in a laboratory being held by an experimenter's hand here, how is this mouse a model? What did we say last time? Why would we call this a model?
Because we test stuff on them.
We test, so
See
what?
how it works on us to see how.
So that example, if I understood you were saying, we test things on the mouse to see how it works on us. Is that what you said? Yeah,
I would say it works as like a control and an experiment.
Well, what do you mean by a control?
It kind of sets the baseline. Depending on what the experiment would be, it would set the baseline of how far it goes from where it was originally to base the effect it has.
So, I think what you're getting at there is if I was running an experiment on a mouse, I might need two populations of mice. Maybe one that don't have whatever the treatment is applied and one that do. And the ones that don't have it applied, you say, well, why are you just keeping mice that you're not doing anything to? Well, it is a model for what would be normal because combining both of your answers together, if I can't experiment on, say, the target system, at least not yet, I might look for a surrogate. But the surrogate, I just like I don't look like those fashion models, I don't look like this mouse. And so you could say, well then, how do I tell that I've made a difference? Well then that's a good point. I might need to have a control. I may need to have two mice. One that doesn't have it applied, and that's my baseline, and one that does have it applied, look at the difference, and then I make the inference that maybe I will see a similar difference if I were to move into, say, a human trial. they're just using kind of a pharmaceutical example. So it is a model because it is answering a what-if question, but we're not necessarily studying mice, we might be studying us, and that's what makes it a model for us. Similarly, let's say we've got a different laboratory scenario here. So we have a woman that is connected through, looks like some respirometry equipment, walking on a treadmill. And so is this a model system? So now I've moved from the mouse actually to a human being. So would I call this a model? Why or why not? Any thoughts? Wait for, yeah.
I think it depends on what the goal is.
Okay.
Like she's undergoing this testing, like in order to compare that to like how it be for the whole population and in the model. But like if she's just trying to get like her own kind of like parameters on just herself, then it's not a model.
Okay, so that's a very interesting answer. So the thought is here is it depends on what the outcome of the experiment or what the question is. And so if the question is, are we making an inference about a population here, then maybe she is a model for the rest of the population because we can't experiment on the whole population, so we pick one of them and we experiment on them, and then we just hope that we can generalize. And then, but if she instead maybe was going in, maybe she's an athlete and was studying her own performance, maybe she came in and this is part of a medical examination and she wants to learn about herself. And in that case, we're experimenting on the target system. So maybe then it's not a model. Now, does anybody, now in that latter case, the maybe it's not a model argument, can anybody argue against that? Why would, let's say she's here for a medical exam and so she's interested in herself. Why would she still, even though the target system is herself, might be considered a model? When you go in for these sorts of tests, do you do, what do they usually tell you like the night before? Or, I mean, do you just come in off the street and just immediately get rigged up to this, or do they usually ask you to do some prep work? They usually,
not eat.
Pardon?
Or not eat.
Sorry?
Not eat.
Not eat, that's one example, right. So they might have you be put you in certain conditions which are artificial. You might have just woken up that day and you were in a bad mood, or maybe you were hungrier than usual, maybe you didn't get enough sleep as usual. So even there, even though she might be interested in some general aspect of herself over her normal day, this may not actually be her normal condition. She doesn't normally walk around with this equipment on her. And so, and likewise, if you ever get your blood pressure taken, if you ever take your blood pressure yourself and then go into a doctor's office, in a wide variety of people, then you find that blood pressure is always higher when it's taken in a doctor's office. So even there, even when you're actually experimenting on the target system, the conditions of the experiment have a level of artificiality that makes it like, it might be much easier to generalize. Certainly, a woman of her age, if we were interested in the population of women of her age or her herself, it probably wouldn't make sense to experiment on me. I might be a different age, a totally different physiology, different sex, those sorts of things. And so I might not, if you could experiment with her, you'll get much, much closer to your target system, but you're still never actually going to get there. So whenever you run an experiment, even when you're experimenting on the target system, you're going to make generalizations across space and across time. And this is the best you can do, but you'll never actually know for sure that, like, she may, in these results up here, it may turn out that her heart looks totally fine, or her breathing looks totally fine, but you just may not have excited the particular condition that she came in with. And so just because this test came out negative, that doesn't mean that, that you've definitely cleared her of whatever the condition is. It might have just been bad luck, or it might have been something with the experimental setup. So even then, I would claim that this is always a model, but depending on the question you're asking, the distance from the target system, and thus your ability to generalize, becomes smaller and smaller. So I think we can combine those two things together, where models will live on a continuum, and that's what we'll end up getting into here. What about this? another target system. So here is an overhead shot of a particular intersection. This is, I think this is actually at a spot in India, and this particular intersection doesn't have any stoplights. And so what you're seeing that this traffic is coming together, and there doesn't seem to be, if you look around, actually any collisions. If we were to watch a video of this, you might imagine that it would be slowed down, that they'd slow down a little bit. But on top of that, even though this isn't a traffic circle, you can kind of see that there is a natural flow here, that although there's some people that just pile on down through the middle, it seems like most people start to kind of go around and you get kind of a traffic circle pattern going. So it just kind of self-organizes into that, which I thought was kind of a surprising effect. If you were to ask me what would happen if you had this amount of traffic with no traffic signals, I don't think I would have guessed that this would have happened. So my question here is this a model system? Why or why not? This is, not in a laboratory. This is out in the field. Do I still call this a model? What do you think?
Call it phenomenon?
Pardon me?
Do you call it phenomenon just because it's naturally occurring?
So the good question is, so I would say that certainly this meets the kind of definitions of a phenomena, but you can have phenomena like the outcome of this experiment might be an interesting phenomenon, for example. So, but the question is the experiment as a whole that produces these phenomena, would I call this system or this image of a system a model system? Yeah.
I would consider it a model because it models like people driving and maybe they experimented before that if they go through the middle they're gonna get crashed into, so they're gonna do the traffic system.
Well, yeah, and we don't know why certain people are driving through the middle and certain people are going around. And you sort of made a hypothesis there that you're assuming that people that live in this area may have actually had negative experiences when they tried to drive straight through, and then they start going around. There could be other hypotheses that just it ends up that due to congestion, you just get a natural flow, kind of like if you're walking down Palm Walk or something like that, and it's between classes, you might notice lanes form. And those lanes don't necessarily form because everybody says, oh, we only walk on the right. Some people might, but not everybody. And you get sort of a lane formation. But so now you're starting to at least make hypotheses about what's going on here. But I guess the fact that we're even making these hypotheses and saying that it's not clear what's going on here, but this is a data point, suggests to me that this is a model, because I didn't know ahead of time what possible outcomes could happen here. I could come up with the explanations, but now I see this, and this data point changes the way I think. And if something changes the way you think, that something was probably a model. This is a model for what happens when you set up this condition, which you may not have ever thought about before. So if you were to ask, what if you had a highly congested area with no traffic lights? You'd say, I don't know, I'll make a couple of guesses. In this particular case, you can say, well, in this case, in this spot, then this is what happened. I don't know if I could generalize. If you did this in Tempe, it may not work this way. There might be cultural norms in this area that makes this more common, and maybe in a Western country, then this wouldn't occur. But this is an example, at least at some places, you get this sort of phenomena, and it makes us then cycle back and start asking new questions. Why does this happen? Is it because people have had a history here, and so they intentionally try to drive in a circle, or is it for other reasons? So that's why I'm saying this is a model, because it is reforming the way we're thinking. It's helping us answer these what-if questions. Likewise, the Titanic here. So you can kind of anticipate where I'm going with all of these questions. The Titanic, I would say, is also a model system. Because before, when they built the Titanic, they thought they knew a lot about how these ships worked. But when the Titanic sank, they learned a whole lot about when you build ships this large, you put them in very frigid waters, and you then put them in areas surrounded by large hunks of ice. And initially, they thought that the Titanic just rammed into a big hunk of ice, and that's what caused it to crack. But it turns out that later on, they've done more recent evidence, and they found that the metal that was used in the hull of this ship becomes extremely brittle at very cold temperatures. And if you were to put the equivalent of an iceberg in, say, warmer waters, then this probably wouldn't have happened. But the combination of cold waters, this particular metal, and those icebergs then ends up setting up the perfect conditions for this to happen. So this is every time we deploy something in the real world, whether the people who are within that system know it or not, they are participating in an experiment. They may not have given their consent, but whether we like it or not, we're going to learn something from this, and we're going to change the way we do things. So engineering or deployment or whatever you like to call this is experimentation. If we were to do experimentation within the bounds of the university, then we would be required to make sure everyone, every subject in the experiment gave their informed consent. That's just a part that if you get government dollars to do research in this country, then you must make sure that anyone you're doing research on gets informed consent. If I wanted to do a study on you, like say I do something different in my teaching and I want to, I'm interested in how that would change and I want to publish a paper on it. In order for me to publish that paper, because the university gets those dollars, I would have to go through a review process to make sure, and then I would also have to get your consent. So if you ever go into a class where they do a study, you'll probably have to fill out a survey that says I'm okay with being in this study. But when you're building when you're in a commercial entity like this and you're not getting government dollars, you don't need to get formal informed consent. There's no law against it. And so you end up experimenting on people, whether or not you call yourself an experimenter or not. And the things you deploy end up being models for how things work. Because the scary thing is when you deploy something, you may not actually know how it works. When you come up with a new traffic timing sequence, you may not know exactly how it works. You're just taking a guess that it's going to work okay. And then you just try it out, and we iterate. And so, this is sort of my saying that the people on the Titanic were effectively these lab mice. The lab mice don't give their consent as well. And so we are okay with that, within even federally funded work. And we are implicitly okay with this. So it's just something to think about when you deploy things. And another example of that I like, this is sort of a case study here, is anti-lock braking systems. So I'm guessing just by making an inference about the ages of you folks, but I'm guessing that those of you who know how to drive learned to drive on cars that had anti-lock braking systems or ABS systems. How many people, if they've slammed on the brakes, have heard kind of like a hum from the front of their vehicle they don't normally get when they press on the brakes, and the brake pedal might be a little softer and the car comes to a quick stop? How many people, as a show of hands, are familiar with that phenomenon? Right, so those are your anti-lock brakes kicking in. So basically there is a system in the front of your car that detects whether you're trying to stop quickly and prevents wheel slip. And so the back in the old days, before ABS, if you slammed on your brakes, there was a chance that if your wheels stopped, your car would start sliding. And once your car is sliding, so the wheels aren't turning but your car is moving, you have no control over it. So you want to prevent that condition. And so when you had to stop quickly, you had to manually pump your brakes. You never put your foot all the way down. You put your foot down, you lift it up, you put it down, you lift it up, and you had to do that manually. And if you didn't do that, you get into a slip condition, and it might be even worse than if you just put your foot all the way down. You were trained to do that when you learned how to drive. Nowadays, we don't have to worry about that because the computer does it for us. But when they released this technology, the old folks that learned how to drive with the manual way were really worried that the computer wasn't going to be able to do it as well as they could. So they had this fear that ABS will not work as well and may increase their risk of a front-end collision if they were to drive with ABS. Now, it turns out that after they released ABS, they actually did see an increase in crashes immediately after cars started being deployed on the road with ABS. And that validated people's fears that maybe these computer systems were not as good as the humans at pumping the brakes. But when they actually looked closer at the data, they found out that these crashes, if you looked at the pairs of cars crashing into each other, the ones with the ABS were not the cars in the back, they were the cars in the front. The cars with ABS were getting rear-ended. And the reason they were getting rear-ended is that they stopped faster than the cars without ABS behind them. So you did actually put yourself into a riskier position by getting a car with ABS, not because the ABS was bad, but because it was too good. So until you had enough market penetration, then you actually were putting yourself in a riskier situation. But if you cut to a time where you have enough market penetration, then where all the cars have ABS, then you'll actually be in a safer world. So this was a model here that people had to update their mental models to show themselves that, for one, they didn't really anticipate, they were thinking too far ahead of time, and they weren't anticipating the initial increase in crashes that they were going to get when they deployed ABS. Because they didn't think about this issue, and they didn't think about how you're going to market this to people. And they just, this whole idea of needing to worry about market penetration, this is similar to like immunization or herd immunity. Like once enough people have ABS, you actually probably don't need ABS so long as most people have ABS. Once enough people are immunized, you probably don't need everyone to be immunized, again, just as long as enough of them are. And so this whole process, this experiment, this real world experiment, changed the way these engineers thought about that. And now they're using this model as a way to think about further automation systems. Like once you go to cars that start braking for you when their cameras detect a bad condition, et cetera, et cetera. So they need to think about, like, we can't just be in a mode where everything is autonomous. We have to think about that mixed case where you've got some autonomous and some human driving, because that may actually be a really difficult situation. So are there questions about that? Does that make sense, that this idea of experimentation? And I've been using these engineering examples, but this goes with plenty. If you go off and work in a policy thing, you need to deploy some policy, you might have to wait for people to, recycling, for example, or something like that. It's sometimes encouraging one person to do it isn't necessarily going to be enough, but encouraging a lot of people to do it and getting them all to do it simultaneously, that is sort of what's in your mind. But in order to get there, you've got to go through this transient. And so it's just sort of this example where if your assumptions are that everyone does the thing, then that might be not a good assumption. That might be like the fashion model case. And so we may need to then think about these transient cases, which may not be that exciting, but are very realistic, and we have to get through. So that's kind of what these kind of tell us. All right, so then other things, would things be a model? So can pictures be models? So this is a picture here. If you were to look up, so this is what's called a funnel cloud. And this is the classic beaver tail cloud formation. So even here, they use another, I would claim this is a model, beaver tail. So in your mind, you picture a beaver's tail, and that tells you what this might particularly look like. But so a funnel cloud is a weather phenomenon we don't see a lot here in Phoenix, but if you move into an area that has a lot of tornadoes, then you've probably at least once in your life seen a funnel cloud. And these things, they're kind of creepy. They're like these tentacles that come down from the clouds, and they precede the formation of a tornado. And so you can show somebody a picture of this, and then the question is, how is this picture a model? Similarly, there are these other phenomena called a wall cloud. And you can see that you can look across here and you can see these things, and you can kind of see why it's could be called a wall cloud. And these also are related to these very dangerous tornadoes. And so a funnel cloud is sort of your average tornado, and a wall cloud means that it's like a really big funnel cloud, and so there's like a really bad tornado coming up. And once we have a picture like this, then if I were to show you a bunch of other pictures, then it's easy for you to sort of see, like, okay, once you've committed this to memory, it's not difficult for you to look over here and say, oh, there's another one. There's a funnel cloud. There's a funnel cloud. If you just saw one of these without first seeing this one, you might just say, oh, that's just like a weird weather formation, a weird weather pattern. But now that I've told you that this here, this picture is a funnel cloud, then you can look at a bunch of other pictures and immediately recognize other funnel clouds. So even pictures, I argue, can be models. So again, models don't have to be mathematical, they don't have to be computational, they don't have to be lab rats. Even pictures themselves can be models. And so, other examples. So, is the picture on the left informative about these? Now we start getting to a point where the funnel, like, you can kind of, buy that these things might relate to this phenomena, but now it's starting to stretch the model a little bit, and that's why we have terms like wall cloud, because now our model stops kind of working. It doesn't capture all of the phenomena, and so we need sort of additional models to be able to predict what goes on here. And even the term funnel cloud, it makes you think of a funnel. And I hope you can sort of see that if I have a funnel plus a cloud, these words, then in your mind's eye, you start predicting something that looks like this. So words are models. You could say, well, what if there's going to be a tornado? Well, they told me that if there's going to be a tornado, it's preceded by a funnel cloud. And then somebody said, what's a funnel cloud? Well, if you don't have a picture, you say, well, it kind of looks like a cloud formation that looks a little bit like a funnel. And that person knows what a funnel is. So then now, if they see this, they're saying, oh, I've never seen a funnel cloud, but I think that's one. So words and pictures can actually be models. And so the last kind of example on this picture side here is going back to that respirometry. I can draw a graph like this. And so I can have this graph has got exercise intensity on one side and oxygen consumption on the other. And this graph has a bunch of these, it's basically these two straight lines and these regularly spaced red dots. And what I like about this is it's a model for so many different things. This model is saying the red dots, they don't add anything useful to the picture in terms of like quantitative information because they're fictitious. They're just placed at regular intervals along this line. But what it communicates to me is that if I were to take data on a real person, there would be points that fall along this line. And so this is a model of an experiment itself. And then the line itself is also a model because we're saying that we think in our model of how the physiology of say a vertebrate system works, that you're going to, as you increase your exercise intensity, you will increase your oxygen consumption only up to a point. And that point will be the so-called VO2 max. Now this is just an idea. Now this has been tested and this is consistent with data that we have on all sorts of vertebrates out there, including humans. But initially it was just an idea. And if somebody would say, well, what is your idea? What do you think is going to happen? Then they're going to say, well, all right, this is what I think is going to happen. We're going to see if we're going to take these data and they're going to climb and climb and climb and hit a point. And then if people actually manage to exercise more and more, they're not going to be able to take in more oxygen. And so their body's going to have to compensate and they're going to start doing anaerobic, or anaerobic respiration. So their other things will change inside the body. So there'll be these two regions and the physiology will totally switch at this particular point. It's an idea, but it is communicating a what if answer to me. What if someone were to exercise and get their intensity increase more and more and more, and you can draw that. And I think that's why we have whiteboards in these things, is people always say, could you explain that a little bit better? What would happen if this? And somebody goes over to the whiteboard and they start drawing a picture, and that picture becomes a model. Just like over here, I have data points here, and so high school GPA on one and university GPA on the other. These are real data points, and somebody's fit a line through them. Now, I'm not saying that there's actually a causal link between high school GPA and university GPA, but it does look like there's a correlation. And so this line that someone's drawn here communicates to me that there is some sort of relationship between these things that we can now talk about. We can say, what if someone had a high GPA in high school? Then we can say, well, we might predict they're going to have a high GPA at university. What does that mean? That sort of starts the conversation. But before drawing this, we don't actually you could come up with that idea. Like, I think the GPA in high school correlates to the GPA in the university, and you might be able to draw this line the same way you draw this line. But then the data ends up communicating to us more confidence in our model because we actually see that the data looks like that as well. So graphs, data, lines, all these things I'm claiming are just as good, just as important models as mathematical equations. So models answer what-if questions. So are there any questions about this statement? Does this be made clear? So you can imagine midterm questions, or I might ask, what's the most general definition of a model, and I'll say like a model has to use mathematics, a model has to use a computer, things like that. And the answer that I will be looking for is something along these lines, that it doesn't actually matter what a model is made up of, it matters how you use it. That makes sense. All right. All right, so why do we, so here's another question for the class then. Well, there's this term model citizen. So what does that come from? Why do we have this? What does that term mean? And why is the word model being used there? Take 30 seconds and talk to your neighbor and sort of say, why do we have this term model citizen? What are possible ways in which model is being used here as a useful adjective? So chat with your neighbor and then come back and I'll see what you guys have to say.
So my interpretation is what whoever the stakeholder is, whether it's the government or whatever else sees as applicable or close to what values whatever the laws what they're when you're trying to put out.
All right, let's bring it back in together. So, what are some examples of things that model citizens do? What is a model? If you are a model citizen, what's
A model citizen stand. Oh wait, you just.
well,
want
just
to-
give me one example.
Okay, what you would do
Yeah.
as a model citizen? I think that you would be kind and respectful. Do unto others as you want them to do unto you.
There you go. So that's one example. Listen, if we were to put a bullet of all the things a model citizen, what characterizes model systems, the golden rule is one example of. What's another thing a model system might do? Yeah.
A model citizen?
Model citizen, yeah.
They file the tax bill.
File a tax on. Good, very specific. Other things that model citizens might do. Yeah. They vote. I like that. That's good. Yeah. Stop at stop signs. These are all, I think, excellent examples. Vote, stop at stop signs, pay taxes, do unto others as you wish them to do unto you. Anything else? I'm sure we could come up with lots of, yeah.
Walk the little old lady across the street.
There's you see someone who maybe is having trouble crossing the street, you help them across the street. These are all, how many people, okay, so those are just a couple of things that model citizens might do. How many people view themselves as a model citizen? Right? It's a fiction. There are no model citizens. We all violate these rules periodically. Maybe we don't vote sometimes. Maybe we don't always help the people across the street. Maybe sometimes we're crappy to people. And so, why is this a useful concept? If none of us are model citizens, then why do we even have the concept of a model citizen? Yeah.
To strive for the ideal of how we want people to work in society.
Okay, so that is one way in which we can define model citizens, is maybe this is prescriptive. Maybe a model citizen is a list of things that someone has agreed on are good things for us to do. So let's say if you have a virtue ethic, then this might be the virtue that you strive to live by. And so this is a list of rules that you're saying that if I am virtuous, then I am going to do all of these things. I may not always do these things, but I'm going to strive to do that. Thus, model citizen in that regard is a what if question about, what if I was a model citizen, what would I do? It is a cookbook for how to be a model citizen. But why those particular properties? Why do we care about people voting? Why do we care about people stopping at stop signs? What is another way in which we can use model citizen that helps us understand where these otherwise arbitrary lists of rules come from? Yeah.
Well, shading is also like a really powerful mechanism, so if we can convince people that this is what they're supposed to do and this is what everyone else is doing, then they might like hop on the bandwagon.
This is sort of, goes along with this idea of what we want people to do. So we're saying, well, how do we get people to want, so we're saying if we publish what a model citizen is, and we all kind of come to agree that we think these are good things, and maybe we can shame people into being these things, and make it like the fashion model that we've all implicitly been shamed that we can't be above a particular weight, well, maybe we can use that for good. But still, why these particular rules? How are these particular rules thought, why is it good for me to stop at a stop sign? Some people don't stop at a stop sign. And, the world seems to go on okay. Some people don't vote and the world seems to go on okay. Why these particular rules?
Because they make society function best. Society functions most efficiently and enjoyably when people follow the genuine rules.
So that's interesting. So there is the idea here is the claim is if we all are model citizens, society will function better. And that's interesting because we might take that for granted, but how do we know that that is actually true? So that's the kind of idea is that just like that VO2 max curve, until we took data, we didn't actually know that VO2 max idea actually was a real thing. But in this particular case, a model citizen, we can start saying things like, that if people behave in a particular way, we can start unrolling that. And we can say, what if everyone stopped at stop signs? Well, now I can design intersections. I can take that as an assumption. And I can say, if everyone stops at stop signs, then I can put stop signs in places that are interesting. Yeah.
So, like a cause and effect becomes very predictable from like a mathematical.
That's right. That's right. So if a model citizen can also be assumptions in a model of society. So not only is a model citizen prescriptive, but before it's prescriptive, the reason why it's prescriptive is that someone else has made a really compelling argument that in some logical way they've unrolled these rules. If everyone behaves in this way, then we get to an outcome that we all agree sounds like a good outcome. So people will say, if we all vote, then we get the leaders that a large fraction of us vote. And that's very logical. In our heads, we buy that argument. Oh yeah, that makes sense. If everyone votes, and then we only pick the leaders according to the vote, then at least those leaders will be, agreeable with at least a plurality, if not a majority of the population. But then, of course, not everybody votes, and you have that sort of issue. But at least the argument sounds good to begin with. So a model citizen is as much prescriptive on what we should do as it is a list of assumptions for a model of society. And so that's really where we initially got the term model citizen, is that it were the assumptions for a societal model. But because we believe in that societal model, then now they become prescriptive. If you run a stop sign, somebody's going to say, hey, you idiot, why'd you run that stop sign? If you would stop at stop signs, we would get the society that we want. And that's effectively what you're saying when you're driving a car. I mean, more immediately you might say, if you're in that car, you could say, hey, I could have gotten hit. But even if you're not in the car, you could say, you're an idiot, you could have gotten hit, and you could have put someone else's life at risk because you ran that stop sign or that stoplight. Now, of course, sometimes you don't see the stop sign. So you have to, in your model of society, if you want to make it more realistic, you have to add a compliance. And so for every list of your model citizen, then you have to have a percentage of stop at stop signs. What's the likelihood of them stopping at stop signs? So, 85%, and so on and so forth. Even a speed limit. When civil engineers and city planners design speed limits, that is not actually meant to be an upper limit. That's meant to be an 85th percentile. In other words, 85% of the people who drive on that road are that limit or below. And so, I wouldn't call it a recommendation, but I would say that when they are evaluating whether they need to add enforcement, they don't ask, did everybody drive the speed limit? They ask, did 85% of the people drive the speed limit? And if they didn't, then they throw in more cops, they do other sorts of things, etc. So that's kind of where we get this model system. All right, so we're going to close this out today with recognizing our mental models. Then we're going to start an exercise that will be due Sunday. You submit it on Canvas. A lot of you will probably even finish it today. I want to focus on a particular type of model, mental models, before we go into starting to get more quantitative next week. So I show you a picture like this. What do you see? So take 30 seconds, talk to your neighbor, and chat about what you see when you look at this picture. What are just some of the things you see?
But like even the ones that
All right, I'm hearing excellent diversity of ideas. So let's pull it in, and so what are some examples? What are the things that come to mind when you look at this image? I heard some things about magnets. What would you say there?
Oh, three magnets holding up a piece of paper.
All right, so I hear, just looking at this without me giving any other background information, this narrative of three black magnets holding up a white piece of paper. Anybody else? Pac-Man. So I assume people are familiar with Pac-Man. So what do you mean by Pac-Man?
The black things look like Pac-Man.
Okay. And then go ahead.
Adding on to her Pac-Man theory, I felt like maybe all of the most strongest Pac-Man of the Pac-Man universe came together and formed this like Pac-Man Trinity.
Pac-Man Trinity. So we're adding, there's a rich, I would like to watch that movie. Like there is a rich story developing here from this picture about the three strongest Pac-Men coming together. I've heard, believe it or not, when I ask this question to other students, some people come up with a story like there's something hidden in the middle that they're all searching for, and they go on, it's a very long and intricate thing about why they're coming together and they're entering a room. A lot here that's not immediately on the page. Anything else? Other things that you see? How about from this side of the room? Five conjoined shapes. So what are the five?
The one triangle that's facing up, the one triangle that's face down, and then the three circles that are.
All right, so I got five. So I hear five shapes that are conjoined. A triangle here that's up, a triangle here that's pointing down, and three circles. So that's interesting, especially because if you really stare at it and squint, you realize there's actually none of those shapes, right? This is not a full circle, that's not a full circle, that's not a full circle. These lines are actually drawn, but they're not completed. And this triangle here is not actually drawn, it's the absence of something there. And yet, when you look at it, I think it's totally acceptable to say there's five shapes to this. Anything else?
That Star of David.
Star of David. So that's another example of a shape that you're inducing in your mind that is, looks like a 1, 2, 3, 4, 5, 6 pointed star, but there's no actual star there. I heard other people talk about a white piece of paper. How many people had a narrative that had involved a white piece of paper on top of something? Anybody? You're talking about a triangular something sitting on top of other things? So you got imagine a white triangle maybe sitting on top of some other shapes, preventing us from seeing those shapes. So none of you all came up I'm just listening around and there are more ideas than that. You all came up with these really interesting ideas of what could have produced this. Your mind, I'm claiming this is not a model, but you had models in your mind that you have used, built up over years of experience that have allowed you to ask yourself, what causal processes could have produced this right here? Your minds answer that what if scenario. What if I encountered this in real life? And you'd say, well, maybe I live in a world that has 3 Pac-Men that come together. What if I live in a world where somebody took this shape and they set it on top of that, et cetera, et cetera. So now we've moved from the picture being the model to the picture uncovering the hidden model that is in your head. So let's go to a different one. What do you see here? So just staring at this without even chatting at it. So what are some descriptions of the image that you see on your right here? How would people describe that?
A man's about to fall through the floor.
How many people see a man about to fall through the floor?
Yeah.
All right, a lot of agreement there. Anything else that you see? Pardon? Is he asleep? Maybe a sleeping man.
Or at least they're behind his back.
An armless man, a man with arms behind his back. If the man is about to fall through the floor, what is the shape of the hole that he's going to fall through? A circle, a perfect circle. I heard somebody say ellipse. What, does anybody have any opinions about the disposition of this man? Is this somebody you would like to be friends with?
No.
I hear a lot of no's. You're condemning this poor fellow who's about to fall through the hole and you haven't even met the guy. So we can keep going here, but the interesting thing, if we look through this, there is not actually any closed shape underneath here. But I think those of you who said, well, there might be somebody underneath the floor that's cutting this hole out with a saw. Some people, like most of you said this was a circle, but if you actually look how wide this is and the way it's drawn, you see that, well, it's much narrower in this direction than it is in this direction. So it's drawn as an ellipse. But in your head, using a mental model, you sort of say that, well, based on the positioning of the feet of this person, I imagine that based on my perspective, I'm perceiving it as an ellipse, but it is actually circular. But there could be other angles and things like that. So that might be going out on a limb, so to speak. You call this a man, but these are weird proportions. This cartoon, to me, is not a really great anatomically correct, version of a human being. Look at this nose. I mean, I have a large nose, but my large nose does not quite match what's going on here. The tiny little head here, the ear, the things don't quite match, but yet we see a person. So this sort of shows you that you're doing a lot of work in your head to make sense of something that logically, if a computer were to look at this, they would not come up with any of the things that we all can agree on. We have a shared mental model about the narrative that's going on here. Similarly, this is sort of a famous painting here where I think it's in the Louvre right now, that you can see this what I think we all can maybe agree looks kind of like 2 bicycles where they share the front wheel. And in French, up top here, this is basically saying that this is a model for those that have just gotten engaged, for those that are starting a long relationship with each other. And down here, where the back tire is linked together, then this is for a couple that is about to get divorced. And so if you look at this, you say, oh, I get it. It's like here, I've encountered someone who I want to spend the rest of my life with. I am as close to them as possible, but I want to be closer. And I can't even be more closer to them, even though I feel like there is a gap between us that I just can't help but to close. And so this captures that feeling even though it's just these two bicycles together. Likewise here, you're at the end of a relationship and you're stuck with someone. You can't get away from them, but all you want to do is to get as far from them as possible, just by flipping the bicycles around. And so I look at that and it communicates an idea, even though none of that idea is really on the page. And then they actually built these things. And so this is actually, I was going to say a model. This is actually a real instantiation where somebody's put together a bike that looks this way, mimicking this here. But I didn't have to build this to know that this would not actually be a functional bike, because I know in my head how a bicycle works. And I know that if I tried to operate this bike, it would be very difficult for this thing to actually work. So it's an example of how we're using our mental models to make sense of these things. Likewise, if I show you a picture of a fishing boat, and you see this one back here, this individual driving the boat using this rudder, then you can imagine how you might drive that boat. Now, if you've never sat in such a boat, if you've never driven a fishing boat like this, then you might say, well, I'd like to turn the boat left. And based on your mental model of, say, driving a car, you might push the rudder to the left. But after you've done that, because there's sort of a reverse action here due to this fulcrum, the boat might turn the wrong direction. So you would need to update your mental model and say that, oh, shoot, when I'm driving in a boat, when I want to move left, I actually have to move the rudder right. And so how many people have seen the movie Independence Day with Will Smith? It's now becoming an old movie. So there was a scene in which he gets into an alien vehicle. Someone has taped a piece of paper to the front telling him which direction is forward and backward on the stick, and they've taped it upside down. And so he pushes it forward, and they go flying into the back, and they hit the back of the area that they're taking off from. And he says, some jerk, they got it backwards. He flips the paper around, updates his mental model, pulls back, and then they take off. And I think sort of a similar thing goes on here. We have a mental model. We don't know necessarily what's going on under the surface, but we have an idea about how to drive this boat. And if we're wrong about that idea, we update our mental models, and we're off on our way. So mental models are extremely powerful and extremely flexible, but they have limitations, which is why we build the other types of models that we'll talk about for the rest of the semester. So if we read this passage here, what I enjoy is I've been using this passage for many years, and the answers I get to the question that will come up here vary as the age of the students vary. And they've actually done a study on this to show that this holds over decades. And so the situation here is a man and his son are driving in a car. They get hit and they into a fatal accident. The man is killed instantly. The boy is knocked unconscious, but taken to the hospital unconscious. The doctor sees the boy in the emergency room, looks at the boy and says, I can't operate on this boy. He is my son. And then so people would ask when this came up, what's going on? And 20 years ago, people had no way to answer what was going on here. So how do you sort of explain this situation? How would the doctor, the boy's father is killed, and the doctor claims that the doctor can't operate on the boy because the boy is the doctor's son. How do we explain that? Yeah. The doctor is his mother. It's easy, right? But in the 70s, when we would give this up for like modeling examples, people would stare at this because their mental models were such that an emergency room doctor would always be a male. They did not live in a world where this could happen. Now, the interesting thing is there is another possibility. The emergency room doctor might be a male. I gave this question to a SOS 212 class, say, a year, maybe two ago, and the first answer came from the room and said the couple was gay. And so that also is something that probably wouldn't come up in the 70s, right? Because people didn't have a mental model where that was a normative thing. And now, it does, which I thought that's great for gay rights, but man, women's, rights is just obviously struggling here. So the fact that that was the first answer that came out. So older audiences often cannot make sense of this. Younger audiences don't see any puzzle, right? I mean, you seem to sort of like actually almost seemed offended that I was asking. And I think.
It's not like people couldn't make sense of this.
Right, yeah. But there's papers written about this situation. I didn't come up with this. I copied and pasted it. So all models are wrong, but some are useful, and that goes for your mental models too. How useful was your mental model? I'm assuming that a large majority of you read this and didn't see a problem, which meant that you've got a mental model that can incorporate this into your worldview. But once upon a time, if you had a time machine and you brought people from the 70s into here, then they might go into an emergency room and they would use these cues, say from people's gender identity, to sort of assume that they knew what role that person had in that. But now we don't have the same correlations between gender identity and the role that they're playing there. So just shows that mental models do change over time. So mental models are a tremendous store of information. You guys took, not even circles and triangles and turned them into narratives about the most powerful Pac-Man coming together. And that shows that you're adding on huge amounts of information that were just not in there. But their weakness is they have trouble handling complexity and dynamic change. And so once you add a lot of components, then you might be able to come up with a narrative about how things work now, but when you predict how things are going to work in the future, it may not work out. So in the 70s, somebody could have understood how an emergency room worked, but if you ask them to predict what an emergency room would look like now in this decade, then they might not be anywhere close. So mental models sometimes have to be put aside, and that's where we get these quantitative models. They're much better at handling complexity and dynamic change. They can be unrolled over long periods of time. The downside is we have to choose what little information goes into them to make them tractable. And that's the reason why social scientists will often criticize systems theory in general on mental models, because from the social sciences, there is a culture where you embrace all of this vast history and you make a statement about now, and you don't even try to make predictions about the future. And thus, they look at these and say, this is far too simplistic to describe a population. So what are the uses of this quantitative modeling? And so there's three major uses I'm calling inference, narrative, and prediction. So when I talk about prediction, those are the ones we're most familiar with. When you turn on the weather to figure out what the weather is going to look like for the next 10 days. The weather person might say, we have models that predict that next Tuesday it's going to rain. And so you've already heard that, they've got a computer model running somewhere, and it takes the current conditions and it unrolls them a couple of days, and it says that based on where the clouds are now and the moisture and everything else, that we predict there's going to be a cloud over Tempe on Tuesday, and there will be a such and such chance of rain. So that's predicting what's actually going to happen based on data that you have now. So that's one use of quantitative modeling. But we also can make inferences. And so a prediction is looking forward, and inference is kind of looking within. And so I've taken a bunch of data, and I can't make sense of the data, so I build a statistical model. And that statistical model shows me that there is a relationship between these two factors. So I might have a GPA in high school and GPA in the university, and there's a relationship there. So by inference, I'm inferring something at a lower order level, so at a simpler thing from a complicated piece of data. So once I get enough data, I see a pattern and I make an inference. And so inference is related to experimentation. I experiment on something, I get data, and I come up with a model that explains that data, and then I use that model as a surrogate for the real world, because I don't know what's going on in the real world. Like, I don't actually know what makes up physical matter, but it turns out a model that incorporates electrons does a pretty good job fitting the data. So I make an inference that I can just assume that electrons exist, and I don't actually care if they actually do or not. And the third use is narrative. So sometimes I have already a good idea of what's going on, but I don't want to use the math that I've used to make that result, because I know it's just not gonna, I'm not gonna sell the idea. And so I have to come up with an alternative model that makes a convincing argument, albeit maybe not as precise as one. So this was an example back when Obama was president. He had this recovery plan where he was a huge stimulus package went into that would basically pump government money into a number of different ventures to try to get the economy going. And so they drew graphs like this that, so here's back when they were going to start the stimulus, and this is projecting forward to 2014. And they've got this, this dash, and this percent is this unemployment that's plotted here. And they show here is our predicted unemployment with the recovery plan and without the recovery plan. And so now they've made a much more convincing argument that, because somebody could say, oh yeah, I believe you that unemployment is going to go down if you pump money into the economy, but how much is it going to go down? Well, by showing them this model here, by showing them this, graphically, then you can see that, oh, actually, it cuts unemployment quite a bit, and it does this over a pretty large envelope here. And so that makes a much more compelling argument. So we can use models as narratives. Sometimes you already have the result in an Excel spreadsheet, but if you animate it in a simulation, people believe it much more than just seeing a column of numbers. Now, that can be misused as well. So here is a plot here. This is data. These are from 1900 to 2010. Up here, this is carbon dioxide in parts per million. We see the red line is global temperature. There's a blue line that's kind of hidden on top of because the green line is overlapping it. The green line is at a particular location in Antarctica. The blue line is in Hawaii. So this is showing that we've got a global trend and a trend in Antarctica and a trend in Hawaii, and they all seem to kind of agree. And you can see that they are, this is increasing pretty convincingly. But that's over this long time window of 110 years. If I were to instead zoom in on just this section right here, then this global thing here doesn't look like it's increasing very much. In fact, it looks like it might be decreasing a bit here. So by massaging the data, by showing only a little piece of the data, that's just as bad as making kind of bad assumptions, as you can end up telling different stories. So we can manipulate these things to tell a different story. And that's why we always have to be careful about listing our assumptions or asking for assumptions if they haven't been given. So these quantitative models take a bunch of different forms. Now, I guess before I go on, are there any questions about this? These three different forms. Is it clear what I mean by the difference between prediction, inference, and narrative? Okay. So analytical models are something that is kind of similar to what you'd see in SOS 211. You form a differential equation model, and you use mathematics, and you can solve that differential equation model, at least in some sense. This solution over here, I'm not asking you to read it or understand it. It kind of actually proves my point that I'm about to make here if you don't understand it. This is a description of what the steady state value of a population that's been infected with a disease over a long period of time. This will tell you how many people will have been infected, how many people will have never been infected, and how many people will have been infected and recovered based on this model here over a long period of time. This does not tell me what the trajectories look like, how quickly people get infected, how quickly they cure, those sorts of things. That is not in this here. It's just the steady state value, what happens after long periods of time. And so the strengths here is that I get an exact solution out of this analytical model. The weaknesses here is that this can be difficult to solve and even worse to communicate. If you were to just put this in an article, like in the New York Times or something like that, you're just not going to be able to make your argument. And then likewise, this also can only describe static or equilibrium phenomena, long time scale phenomena. Numerical methods, like you put in a spreadsheet, do a little bit better because you can plot out the same sorts of models with graphs like these. Like if you did these logistic growth models in SOS 101, then you might have gotten these sorts of things where you see populations and you don't only You not only know where they'll be in the end, but you also know what will kind of happen up until that point. But once you put things in these numerical methods, like these spreadsheet formats like this, it's difficult to imagine changing them because you have to edit a bunch of formulas and you're not really communicating the underlying process here. The graphs are good, but the structure of the model doesn't really communicate what the model looks like. And so that's why we go to these simulation methods where we can actually draw models in a computer sim that are very easy to interpret, or much easier than the math. We still get the same sort of plots out. We don't get the exact solutions we get out of a mathematical model, but we can play with these and make modifications much more quickly. And this is the realm of what we do all semester. So there are three major simulation methodologies: agent-based modeling. Marco Jansen teaches a couple of courses in ABM if you're interested in that. Discrete event system simulations, I teach some courses in that. And then also over in the business college, I teach courses of that, and system dynamics modeling. And so we're not going to focus on these. So when I talk about simulation this semester, just know that there are other types of simulation. They work in a similar way, but we use different constructs within them. So these constructs are going to focus on things that we can model as smoothly varying quantities, as opposed to things that where we're modeling like every single individual in a system. So system dynamics modeling, this method, it's a branch of control theory applied to socioeconomic systems and management science. It focuses on problems in which time is an important factor. When we want to know what happens over time as opposed to just at the end of a time or what's happening just now. It's how we unroll things and we care about the entire trajectory over time. So by the end of the class, you'll be familiar with behavior diagrams like these and the types of system structures that produce these. And using your familiarity with that, when you draw new systems, before you even simulate them, you'll be able to make a guess at what those systems will do. And if you simulate them and they don't behave in these kind of prototypical ways, then that identifies there's something really interesting going on in your particular implementation that's worth further study. So that's basically an overview of what is a model and how it's going to apply. We're going to get more quantitative and start building these models next week. And as we close here, are there any questions? Yeah?
The three approaches to modeling, like the agent-based modeling and the system modeling, are those like types of simulation?
These are all three different types of simulation. Yeah. So there are, like NetLogo is a tool typically used for this. There are a bunch of tools for this discrete event system, like AnyLogic is one of these, Arena, there's a bunch of different models here, and then we will be using VinSim and InsightMaker. There's other tools for system dynamics modeling like Stella, that's another popular one. So there's a bunch of different software tools that are designed for these different sim models. Once you get used to one type of sim, it's easy to wrap your heads around the other type of sim, but it's kind of like learning a different programming language. Once you're using Excel, if you want to then go to C, then that might be kind of a big jump, but you at least buy into the fact that programming might be useful. All right, so where I want to close things here is, we don't have a lot of time to start on this, but if you go on to Canvas, there are 3 questions, and those 3 questions basically are like the mental model questions we did here. I'm going to show you 3 images, and I'm basically asking you, identify the mental models that you're using to make sense of these images. So if you're to go onto Canvas, for the last couple minutes of class, you can feel free to give this a shot. This shouldn't take you more than a half hour to complete this assignment, but it is due Sunday night. Just concise answers in your own words that capture this, what you think is going on when you're making sense of these things. And then there is a muddiest point due Sunday. So that's just the thing that's sort of like, what are the highlights of this week from your perspective? And then start reading chapter 1, because we'll go over chapter 1 on Tuesday, and we'll start Tuesday with a 10-minute kind of quiz over chapter 1. And there is a reading exercise, there's a couple of questions about chapter 1 due Monday night that's just sort of to help you lead you through the chapter. So any questions about that? All right, so the last thing then is the attendance exercise. So so do the same thing we did last time. Either go to this URL or scan that QR code, or tear off a sheet of paper and put your ASU Write username up here. And the question that I will ask is, what type of model capitalizes on your personal experience, but is very bad at making predictions of complex systems into the future? The question is, of the types of models that we talked about here, what is the kind of category of models that capitalizes on a person's individual experience over their entire life, but is very bad at predicting what might happen in the future for very complex situations? I'm just looking for like 2 words where the second word is models. And otherwise, that's all I've got for you today. So if you'd like to log into Canvas and work on that, I don't think people didn't start coming in until at least 15 minutes later. So you probably could knock out that whole assignment if you've got the time. And I'll hang around as I clean up here. Yeah, I'm just looking for what's 2 words that describes the category of models that capitalizes on your own personal, individual experience of your whole life, but is very bad at sort of predicting the outcome of complex systems over time.
Got it. Thank you.
On Canvas, it says it's on this.
Oh, shoot, yeah. Oh, you know why? Because I think it will automatically unlock the end of class. I meant to unlock it in the middle, so that's my fault.